Hello and welcome everyone to our weekly session titled Latest in Bitcoin Tech, where we go through the Bitcoin Optech newsletter. And this week we will cover newsletter number 340, published on 7th of February 2025. This week's newsletter has a news section, as the name suggests, which is quite lengthy. In fact, this week's newsletter is probably the lengthiest I've seen in recent times. And obviously, due to time constraints, we will not be able to cover the entire newsletter, but we will choose the topics that I believe would be of a good interest or better interest to the listeners and the joinees. Then we have this new incorporation called changing consensus. I believe this is a monthly feature of changing consensus. We'll see if we can take up something from this. And other than that, we have the two irregular sections, releases and release candidates, and notable code and documentation changes. Before we delve into the newsletter, let's go to the preface and familiarize ourselves with what the newsletter contains this week. This week's newsletter announces a fixed vulnerability affecting LDK, summarizes discussion about zero knowledge gossip for NN channel announcements, describes the discovery of previous research that can be applied to finding optimal cluster linearizations, provides an update on the development of the Erlay protocol for reducing transaction relay bandwidth, looks at trade-offs between different scripts for implementing LN ephemeral anchors, relays a proposal for emulating an operand opcode in a privacy-preserving manner with no consensus changes required, and points to renewed discussion about lowering the minimum transaction fee. So as you can see and make out from the preface that there is a lot of content in this newsletter. Let's see how much of it can we cover. We have slightly above 50 minutes with us. So the first one being channel force closure vulnerability in LDK. For those of you who don't know, LDK is an implementation of the Lightning Network. Matt Morehouse posted to Delving Bitcoin to announce a vulnerability affecting LDK that he responsibly disclosed and which was fixed in LDK version 0.1.1. Similar to Morehouse's other recently disclosed vulnerability in LDK, see newsletter number 339, a loop in LDK's code terminated the first time it handled an unusual occurrence, preventing it from handling additional occurrences of the same problem. In this case, it could result in LDK failing to settle pending HTLCs in open channels, ultimately leading honest counterparties to force close the channels so that they could settle the HTLCs on chain. This likely couldn't lead to direct theft, but it could result in the victim paying fees for the closed channels, paying fees to open new channels, and reduce the victim's ability to earn forwarding fees. Morehouse's excellent post goes into additional detail and suggests how future bugs from the same underlying cause might be avoided. Right. So this news article talks about a vulnerability that is specific to one of the implementations of the Lightning Network, LDK. And let us read the article to try and understand better what the vulnerability is that is being brought to our attention. I'll zoom this a little. All right, let's read it. What's the background? Whenever a new payment is routed through a Lightning channel, or whenever an existing payment is settled on the channel, the parties in that channel need to update their commitment transactions to match the new set of active HTLCs. During the course of these regular commitment updates, there is always a brief moment where one of the parties holds two valid commitment transactions. Normally, that party immediately revokes the older commitment transaction after it receives a signature for the new one, bringing the number of valid commitment transactions back down to one. But for that brief moment, the other party in the channel must be able to handle the case where either of the valid commitments confirm on chain, right? So I'm assuming we all know on the surface level how the Lightning Network functions. There are two transactions that happen on chain for each Lightning channel. The first is known as a funding transaction, which is the transaction that initiates the Lightning channel and that adds liquidity to the Lightning channel. And when you intend to close the Lightning channel, you go on chain with that which is known as the commitment transaction, right? So you move from L1 to L2 with the funding transaction, and you go back from L2 to L1 using the commitment transaction. The moment you make a payment or you route a payment on the Lightning Network, you need to update your commitment transaction. Your commitment transaction depicts the latest state or the latest balance of the parties on the Lightning Network. So if two people have a Lightning network, have a Lightning channel open with each other, the commitment transaction reflects the most recent state or the most recent balance that each parties in that channel owns. So, for instance, if Alice and Bob have a Lightning channel with each other, and Alice has one Bitcoin in that Lightning channel, and Bob has zero, and then Alice transfers. So the commitment transaction at this point in time will depict that. The commitment transaction at that point in time will depict the fact that one Bitcoin belongs to Alice and zero Bitcoins belong to Bob. Now, let's say Alice transfers zero point 0.1 Bitcoin to Bob. Now the balance has been updated. Now Alice has zero point 0.9 Bitcoin to her side, and Bob has zero point 0.1 Bitcoin, right? So a transfer has happened. A change in the state of the balance on the Lightning channel has occurred. And whenever that happens, whenever a payment is routed across the Lightning channel, the commitment transaction is updated to reflect the latest state of the balance. So the initial commitment transaction in our example depicted that Alice owns one Bitcoin and Bob owns zero Bitcoin. And the latest commitment transaction after Alice routes zero point 0.1 BTC to Bob will depict the fact that Alice now owns zero point 0.9 BTC. 0.9 BTC of liquidity is on Alice's side, and zero point 0.1 BTC of liquidity is on Bob's side. So every time a transfer or a payment is routed across the Lightning network, there is a new commitment transaction. Now, it's imperative to know that with every new commitment transaction, the old commitment transaction becomes redundant. It is revoked. And at any given point in time, there can only be one valid commitment transaction. We cannot have two valid commitment transactions. However, there is a brief period for which each counterparty in the Lightning Network has a valid commitment transaction. Now, when does this happen? Like, for instance, if Alice routes some payment to Bob, Alice will create an HTLC, right? Alice will create a commitment transaction with this new HTLC, that depicts the latest state of the network. And Alice will sign this commitment transaction and give it to Bob. Or Alice will give this transaction to Bob. Bob will sign this transaction and Bob will return uh, his own signature to Alice, right? Because there are two versions of the commitment transaction. If there are two parties involved in a Lightning channel, then there are two versions of the commitment transaction. Each party has their own version of the commitment transaction, which they can broadcast at their own discretion. So Bob will keep one version of the commitment transaction, and Bob will share his signature to Alice, uh, so that Alice can use that signature to sign her version of the commitment transaction. Now, now the moment Alice gets Bob's signature, Alice usually revokes the old commitment transaction. But there is a brief period during which Alice might have not might have, will certainly have two valid commitment transactions before she revokes the old commitment transaction and she gets Bob's signatures for the new commitment transaction. There's a brief period where she has two valid commitment transactions. Once she revokes the old commitment transaction, then everything is hunky and dory. Then she has only one commitment transaction, as it's mentioned in the example, bringing their number of valid commitment transactions back to one. But there is a brief period during which there are two valid commitment transactions that Alice has. And just in case she broadcasts the old commitment transaction, which has not yet been revoked, then we need a mechanism in place to prevent that from happening, right? So if a counterparty in the Lightning Network has two valid commitment transactions, they might act malicious and they might broadcast that commitment transaction, which is more beneficial to them. So we need to have a mechanism in place. And what's the mechanism in place? We see the number of outstanding HTLCs, right? So if the commitment transaction that has been broadcasted does not contain the HTLCs, which are a part of the latest state of the Lightning channel, then what will happen? Then that HTLC, which is a part of the latest commitment transaction, will fail, meaning the funds locked in that HTLC will go back to the recipient. So if, let's say, In the initial state, Alice had 1 Bitcoin and Bob had 0 Bitcoin, right? And now we update the commitment transaction. Alice has 0.9 Bitcoin and Bob has 0.1 Bitcoin. Now, Bob gives his signature to Alice so that Alice can sign this new commitment transaction with the updated ledger and revoke the old commitment transaction. But Alice uses this signature and signs the new commitment transaction, but she does not revoke the old commitment transaction. Rather, she broadcasts the old commitment transaction, right? Which means that the HTLC, the new HTLC, which Alice shared with Bob, in which Bob is owed 1 BTC, is not present in that commitment transaction, right? So if that latest HTLC is not present in the commitment transaction, that specific HTLC is failed, meaning that that 0.1 BTC that Bob has further transferred on behest of Alice will get back to her. So that is the mechanism that we have in the Lightning Network to prevent people from broadcasting a valid commitment transaction before it is revoked, right? For this reason, LDK contains logic to detect when there's a difference between the counterparty's confirmed commitment transaction and the set of currently outstanding HTLCs, right? So this is what the gist is. So if Alice tries to broadcast a valid commitment transaction, but with an old state, then obviously it will miss the HTLCs, right? It will miss the latest HTLCs. And if those latest HTLCs are missing, then the funds attached with these HTLCs will fail, meaning they will go back to their recipients. Any HTLCs missing from the confirmed commitment transaction are considered unrecoverable and are immediately failed backward on the upstream channel, while all other HTLCs are left active until the resolution of the downstream HTLC on chain, right? So upstream channel is the channel where you are owed funds, and downstream channel is the channel where you have to pay funds. Because the same payment hash and amount can be used for multiple HTLCs, example multi-part payments, some extra data is stored to match HTLCs on commitment transactions against the set of outstanding HTLCs. LDK calls this extra data the HTLC source data, and LDK maintains this data for both of the counterparties' valid commitment transactions, right? So now you need to keep a track of HTLCs, right? You need a mechanism to identify HTLCs on the network. How do you do that? You usually do that with the payment hash. With the payment hash, right? What's the payment hash? So basically, every time you want to make a payment to someone on the Lightning Network, you first request them for an invoice. You first request them for an invoice. So their node will generate a random number, which is a pre-image, and then their node will hash that pre-image and share that hash with you. That hash is what is used as the identifier of the HTLC, and the amount. The two primary pieces of information that are used to identify HTLCs on the Lightning Network is what the payment hash, which is the hash of the pre-image, and the second is the amount, right? But it is possible that multiple HTLCs can have the same payment hash and amounts, right? Because you can create a multi-part payment. You can create an invoice that at once which contains multiple payments, right? So in that situation, your payment hash and amount will be same. So multiple HTLCs can be created with the same payment hash and amount. So how do you distinguish between them? So if I create an invoice that has 10 HTLCs using the same random number, meaning the same pre-image and the same payment hash and the same amount. So if somebody wants to pay me 1 Bitcoin over the Lightning Network, I create an invoice with multi-payments, right? Multi-part payments. So using the same pre-image, I create 10 different I mean 10 different HTLCs, but all HTLCs have the same amount of 0.1 Bitcoin and they have the same payment hash. So how do you distinguish between different HTLCs, and how do you recognize between different HTLCs when they have the same payment hash and the same amount? For instance, in the example that we discussed just now, you have some extra data. You have some extra data. Okay, you add some extra metadata to distinguish one HTLC from the other HTLC, right? It could be anything. LDK calls this extra data the HTLC source data, and LDK maintains this data for both of the counterparties' valid commitment transaction. So there is some unique data, because there is a possibility that multiple HTLCs can have the same payment hash and the same amount. Then payment hash and amount are not adequate information for us to distinguish between HTLCs. We need more than that. And for that information, LDK uses some metadata which it refers to as the HTLC source data, which is unique to each HTLC. Now, there is a catch pertaining this. What is the catch? The catch is that the moment the commitment transaction is revoked, this source data is deleted from the database. LDK deletes this source data from the database, right? And how can this be used as an avenue to exploit to perform a greasing attack? We'll see that further. Once a counterparty commitment transaction has been revoked, however, LDK forgets the HTLC source data for that commitment transaction to save memory. As a result, if a revoked commitment transaction later confirms, LDK must attempt to match commitment transaction HTLCs up to outstanding HTLC using only payment hashes and amounts. LDK's logic to do this matching works as follows, right? So let's say somebody has broadcasted and confirmed a revoked commitment transaction. Okay, somebody has broadcasted and confirmed a revoked commitment transaction. After that, they broadcast another commitment transaction that has multiple HTLCs with the same payment hash and the same amount. How do we distinguish between the HTLCs of the revoked commitment transaction and the valid commitment transaction? How do we distinguish between them? We use that which we call HTLC source data. However, LDK releases HTLC source data from the revoked commitment transaction. So what do we have now? We're only left with the payment hash and the amount, right? So let's just go through this logic and try and understand this, right? So if the commitment transaction is revoked, so a commitment transaction can be in two states. It can either be revoked or it can be valid. It can be in the latest state or it can be in a revoked state. So if a commitment transaction is not revoked and the commitment transaction contains HTLC source, okay, then continue. Then the loop does not fail. Then it continues, right? So if a commitment transaction is not revoked and it has source data as well, meaning it's a valid commitment transaction. And if confirmed commitment transaction is revoked and confirmed commitment transaction contains HTLC payment and hash amount, okay, then again we continue, but we fail the upstream HTLC, which means that if the commitment transaction is revoked, but it has payment hash and HTLC amount, we will fail the upstream HTLCs. Which upstream HTLCs? Those upstream HTLCs which have the same source data, which have the meaning which have the same payment hash and which have the same HTLC amount, right? Note that this logic short circuits whenever an outstanding HTLC matches the payment hash and amount of an HTLC on the revoked commitment transaction. Thus, if there are multiple outstanding HTLCs with the same payment hash and amount, a single HTLC on the revoked commitment transaction can prevent all of the duplicate outstanding HTLCs from being fed back immediately. So if there is a revoked commitment transaction that has been broadcasted and that gets confirmed, okay, because there is a small period of time in which it is valid, there is a small period of time in which it is valid. If it is broadcasted and it gets confirmed there and then we need to ensure that all the HTLCs uh, belong that all the HTLCs that have the same payment hash and the same payment amount should fail, that have the same payment hash and the same payment amount should fail. And by fail, I mean the recipient should get the funds back. The recipient, the rightful owner should get the funds back. Now, since the only way to distinguish between two HTLCs that might have the same payment hash and the same amount is the HTLC source data. And because the commitment transaction is now revoked, we don't have that HTLC source data, right? So what will happen in this situation, what this loop does is that it fails the first HTLC that matches the payment hash and the amount of the confirmed commitment transaction, and all the other HTLCs, all the subsequent HTLCs that might have the same payment hash and amount, they are not failed. They are not failed. Rather, they are left unattended. Okay. So if there is a revoked commitment transaction that has a specific payment hash and a specific amount which gets confirmed, right? Now there are 10, there is another commitment transaction which has, let's say, 10 HTLCs with the same payment hash and the same amount. We want all those 10 HTLCs to fail and the funds locked in those HTLCs should go back to their rightful recipients. Instead of that happening, only the first HTLC that matches the payment amount in the hash fails. And in our example, the other 9 HTLCs that have the same amount and the payment hash for the commitment transaction, they are left unattended. They are left unattended. Now, what could happen in this situation? One could be that they are left unattended for a long tenure of time, right? So the funds of the beneficiaries are locked up. The second scenario would be that the people who owe the funds that are locked in those HTLCs will have to force close the channel, right? Because there are multiple versions of the commitment transaction. So they will have to force close that channel. And when you force close a channel, there is a time lock attached to it, right? There is a time lock attached to it. Until and unless that time lock does not expire, you cannot redeem your funds. So in this situation, what will happen if the counterparty who has two valid commitment transactions broadcasts an old state of the commitment transaction and gets that state of commitment transaction confirmed, you ideally want all the HTLCs of the latest version of the commitment transaction to fail such that the recipients receive their fund back. But that will not happen. Only the first HTLC that matches the payment hash and the amount will fail, whereas the other subsequent HTLCs will not fail. They'll be left perplexing. So the only way for a person who's been subjected to this griefing attack to get their funds back is what? Is for them to force close their lightning channel. And if you know how force closing the lightning channel works, there's a time lock attached to it. So you have to wait for a certain period of time, whatever it could be, that is mutually agreed at the time of creating and signing the commitment transaction for you to get your funds back. More so, another drawback is that you have to pay fee. You have to pay the fee for getting the transaction mined on the network. And if you want to make a payment, then you have to probably initiate another lightning channel. So you basically your funds get stuck for a long period of time till the HTLC expires, till the time lock of the commitment transaction expires of the forced closure. You also have to pay fee for closing the lightning channel, and you have to pay fee for opening another lightning channel, right? Ideally, what you want to happen is that all the HTLCs should fail. All the HTLCs of the latest commitment transaction should fail, and the recipients should get their funds back. But to recognize all of those HTLCs, you need the HTLC source data, which is wiped off the which is wiped off the LDK's data, and that is why you only left with the payment hash and the amount, which only recognizes the first HTLC. The way this loop has been triggered, which only recognizes the first HTLC and fails the first HTLC, and the other HTLCs are left perplexing. The only way for the people who owe funds locked in those HTLCs to redeem is by force closing it and thereby locking their funds for a long amount of time, and also paying mining fee for closing the lightning channel and opening the another lightning channel. So there's an illustration given here. We won't be able to go into the detail of it, right? There's an illustration given here that there is an HTLC. Let's say there are n HTLCs. Let's just read this. Consider the following topology where B is the victim and A 1 to n nodes are all the nodes that B has channels with. M1 and M2 are controlled by the attacker. The attacker routes n HTLCs from M1 to M2 using the same payment hash and amount for each, with each payment going through a different A node. M2 then confirms the revoked commitment transaction that contains only one of the n HTLCs. Due to the duplicate HTLC failback bug, only one of the routed HTLCs get failed backwards. Right, so there are n HTLCs. So all n HTLCs have the same payment hash and the same amount, but instead of all n HTLCs failing, only one of those HTLC fails, while the remaining n minus one HTLCs get stuck. Finally, after upstream HTLCs expire, all the A nodes with stuck HTLCs force close their channels with B to reclaim the stuck HTLCs, right? So basically, this is the griefing attack because you don't end up losing your funds. However, you have to wait for the time lock to expire to redeem your funds, and also you have to end up paying fee for force closing the lightning channel. And if you intend to participate in the lightning network again, then you probably have to open another channel and pay fee for the funding transaction of that channel. What's the fix? Starting in version 0.1.1, LDK preemptively fails back HTLCs when their deadline approach if the downstream channel has been force closed or is in the process of force closing. While the main purpose of this behavior is to prevent cascading force closures when mempool fee rate spikes, it also has a nice side effect of ensuring that duplicate HTLCs always get failed back eventually after a revoked commitment transaction confirms, right? So the fix is that when a revoked commitment transaction gets confirmed, then the latest state of the channel, the latest commitment transaction, which has not been confirmed on the network, all the HTLCs that it has failed, meaning all the funds that are locked in that HTLC are given back to their rightful recipients without them having to wait for the time lock to get expired, or without them having to pay fee to force close the channel, without them having to pay fee to initiate a new channel. So that is what this vulnerability is about. The fact that LDK deletes the HTLC source data after a revoked commitment, after a commitment transaction is confirmed, after a commitment transaction is revoked, right? And then the only way for you to distinguish one HTLC from another is the payment hash and the amount. And if there are multiple HTLCs that have the same amount and the same payment hash, there is no way for you to distinguish between all those multiple HTLCs. Rather, the first HTLC of the latest state of the transaction that your node encounters that has the same payment hash and the amount as the payment hash and the amount of the HTLC in the revoked commitment transaction will get failed, and all the subsequent HTLCs will lie perplexing, and the person who has been subject, who is the victim of this griefing attack, will have to wait, will have to force close the channel, pay the fee for force closing the channel, and will have to wait till the time lock expires so that they can redeem their funds. But the LDK version 0.1.1 onwards, all the HTLCs of the latest state of the commitment transaction after a revoked commitment transaction gets confirmed are failed, meaning they are returned back to their rightful recipients, thereby circumventing this griefing attack. Okay, that's the first news article. That's what I had to share about. I'll just read this in gist, okay, because this is quite a dense article. Like people need to understand in granularity how the Lightning Network functions, what HTLCs are, what upstream HTLCs are, what downstream HTLCs are, what's a payment hash, what's a pre-image, uh, what's a commitment transaction, what's a revoked commitment transaction, what's the handling penalty, what's the time lock, all of these granularities you need to understand. If you understand these things, then you'll be able to appreciate and comprehend the proposal. However, the nature of this session is such that it does warrant at least an intermediate level of understanding of Bitcoin technicals. Some of the topics that we cover are for beginners, are beginner friendly, but then some of the topics that we cover are pretty granular and intricate and require an intermediate level of understanding of Bitcoin technicals. So if somebody from among you was not able to completely comprehend what was covered, uh, be patient. There's nothing wrong about it. This is not a very straightforward topic. This is not a very straightforward discussion that we had. But if you were able to pick up the bits and pieces and make at least some sense out of it and understand some things about the Lightning Network which you weren't aware about earlier, then that's great. That's time well spent. And if you want to further dig into what the Lightning Network is and how it functions, then I recommend you to go through this book, Mastering the Lightning Network by Andreas Antonopoulos, and then come back. I think you should go through chapter number 7 and chapter number 8. I think it's chapter number 8 primarily that talks about HTLC. So go through chapter number 8 of Mastering the Lightning Network by Andreas Antonopoulos. Come back and read this post and listen to our conversation. Maybe it'll make more sense to you. I will just summarize it by reading the summary of this news article so that for those of you who were able to garner sense out of it, it'll just summarize and refresh your memory and consolidate it. Matt Morehouse posted to Delving Bitcoin to announce a vulnerability affecting LDK that he responsibly disclosed and which was fixed in LDK version 0.1.1. Similar to Morehouse's other recently disclosed vulnerability in LDK, see newsletter number 339, a loop in LDK's code terminated the first time it handled an unusual occurrence, right? This is what we talked about. It terminated the first time, meaning the first HTLC that matches the payment hash and the amount, preventing it from handling additional occurrences of the same problem. So if it comes across subsequent HTLCs that have the same payment hash and the amount, it will not fail those HTLCs as it should do in an ideal situation. Rather, those HTLCs will be left perplexing. In this case, it could result in LDK failing to settle pending HTLCs in open channels, ultimately leading honest counterparties to force close. So the only way for honest counterparties to redeem the funds that they owe is by force closing the Lightning channel so that they could settle the HTLCs on chain. This likely could lead to direct theft. As I mentioned, it's a griefing attack. You cannot steal, or an attacker cannot steal anybody's fund, but it could result in the victim paying fees for the closed channels, paying fees to open new channels. Because when you force close a Lightning channel, then you have to pay fee to get the commitment transaction mined. And if you intend to continue participating on the Lightning network, then you have to open another channel, and then you have to pay more fee for getting the funding transaction mined. So paying fees to open new channels and reduce the victim's ability to earn forwarding fees. Morehouse's excellent post goes into additional detail and suggests how future bugs from the same underlying cause might be avoided. That is the first news article that we covered. Which should we take Next, we'll probably go to the cluster mempool one. I'll just have a look if there are any questions, any observations in the chat. And if anybody has anything to share or ask, please feel free to unmute yourself and speak in the middle. I will halt and try my best to answer you. And if there are no questions, then we will move on to the next one, which is cluster mempool. Okay, let's read this. We're at 836. Discovery of previous research for finding optimal cluster linearization. Stephen Richer posted to Delving Bitcoin about a research paper from 1989. He found that he has a proven algorithm that can be used to efficiently find the highest fee rate subset of a group of transactions that will be topologically valid if the subset is included in a block. He also found a C++ implementation of several algorithms for similar problems that are supposed to be even faster in practice. Previous works on cluster mempool focused on making it easy and fast to compare different linearizations so that the best one could be used. This would allow using a fast algorithm to immediately linearize a cluster with a slower but more optimal algorithm able to run on spare CPU cycles. However, if the 1989 algorithm for the maximum ratio closure problem or another algorithm for that problem can run fast enough, it could be used or if the time instead. But even if it was moderately slow, it could still be used as the algorithm that runs on spare CPU cycles. Peter Wooler replied with excitement and multiple follow-up questions. He also described a new cluster linearization algorithm that the Cluster Mempool Working Group has been developing based on a discussion from Bitcoin Research Week in Donging Guo and Alil Zohar. It converts the problem to one that can be addressed using linear programming and appears to be fast, easy to implement, and produces an optimal linearization. If it terminates, however, proof is needed that it will terminate and in a reasonable amount of time. Although not directly related to Bitcoin, we found interesting Richard's description of how he found the 1989 paper using the DeepSeek reasoning LLM. At the time of writing, discussion was ongoing and additional papers about the problem domain were being explored. Richard wrote, "It appears that our problem, or rather is a generalized solution, which is called source sync monotone parametric min-cut, has applications in something called polygon aggregation for map simplification and other topics in computer vision, right?" So this basically is, it talks about a research paper. We obviously will not go into the details of a research paper because of firstly time constraint and secondly because it might not be of interest to everyone. So whoever wants to go and actually read this research paper and what it talks about can do it at their own behest. We will just touch upon what cluster mempool is, what cluster mempool linearization is, and what this algorithm is talking about. Let's just try and understand what cluster mempool is and what it plans to do and what the proposal is. So before we go into what cluster mempool is, right, we all know what a mempool is. Mempool is basically a data structure on your node that stores the transaction or that queues the transaction that are eligible to be included in a candidate block. So your mempool ideally would be around 300 MB and a Bitcoin block is around 4 MB. So you queue up transactions worth 300 MB and out of that your node has an algorithm which it deploys to choose 4 MB transactions, 4 MB worth of transactions out of those 300 MB worth of transactions if you're sticking to the standard policy. Now there are multiple algorithms that your node might deploy to choose which transactions it wants to include in the candidate block. Mostly, most people resort to the most profit optimizing transactions, like all the transactions that have been queued up in your mempool. Your node would ideally pick up the most profitable transactions, the one that are paying the highest fee, and will include that in a candidate block. How like what is like I mentioned that the mempool would ideally be of 300 MB, right? So the space is finite. What if your node detects transactions in excess of 300 MB? How does your node choose which transactions will go into the mempool and which transactions will not go into the mempool, right? Because the mempool is a finite resource. So the transactions are included currently. The transactions are included in the mempool on the basis of ancestor fee rate. On the basis of ancestor fee rate. What's the ancestor fee rate? So if a transaction is trying to enter the mempool, the fee rate of all of its ancestors, all of its unconfirmed ancestors in the mempool will be calculated. So if there's a transaction, we'll see what is the fee of its parent and its grandparent and its great grandparent, all the way up to the ancestry that we can trace. All of the unconfirmed transactions, we'll look into all of that, right? So if there's a transaction, if my mempool is full, if it has 300 MB worth of transactions, now a new transaction comes and knocks the door of my mempool. How does my mempool determine whether this transaction should be included or not? The mempool will calculate its ancestor fee rate. It will see if its parent is unconfirmed, yes, then it will see the fee of the parent. Then it'll see if the grandparent is unconfirmed, yes, it will see the fee that the grandparent is paying. It will see if the great grandparent is unconfirmed, it will see the fee that the great grandparent is paying. So it will see the fee of all the unconfirmed ancestors of that transaction. And if they are paying a good cumulative fee, if they're paying a higher fee than any of the transactions that are already in the mempool, then they will eject the transaction that is in the mempool and make space of for this transaction. And how do we reject transactions from the mempool? Based on the descendant fee rate, right? So just remember this, that we include transactions in the mempool based on the ancestor fee rate. The transaction that is paying the highest ancestor fee rate gets included in the mempool. And how do we decide which transactions to evict from the mempool? The transaction that is paying the lowest descendant fee rate. So we look at a transaction, we see how much fee its child is paying, unconfirmed. We see how much fee its unconfirmed great grandchild is paying, how much fee its unconfirmed great grandchild is paying, and that's how we eject it. So the transaction that is paying the highest ancestor fee rate gets preference in getting included in the mempool, and the transaction that is paying the lowest descendant fee rate uh, gets preference in getting evicted out of the transaction. Now, there's a caveat to this, that no transaction in the mempool can have more than 25 unconfirmed ancestors, including itself. Neither can it have more than 25 unconfirmed descendants, including itself. So, if there's a transaction in a mempool that has 24 children and its 25th child tries to come into the mempool, it'll get kicked out because our limit is what? 25 ancestors, including the transaction itself, and 25 descendants, including the transaction itself. So that is how the mempool functions right now. That is how we determine what transactions enter the mempool and what transactions are evicted from the mempool. Now, there is work being done in order to kind of redo this mechanism, and instead of organizing transactions in the mempool in the form of ancestors and descendants, rather organizing them in the form of a cluster. Now, what's a cluster? A cluster is basically nothing but a set of unconfirmed transactions that are related to each other. So there is a transaction, it has an unconfirmed child, it has an unconfirmed grandchild, it has an unconfirmed great grandchild. Let's say it has 50 unconfirmed children. So all those 50 unconfirmed children will be known as clusters. So we will get rid of this 25 ancestor and descendant limit topology. Rather, we will bifurcate transactions on the grounds of clusters. So all transactions that are topologically via lineage, all the unconfirmed transactions that are topologically via lineage related to each other will be referred to as one cluster, whether they're 25, less than 25, more than 25. And these clusters will be further bifurcated into chunks. How do we bifurcate them into chunks? We will bifurcate them into chunks depending on their sizes, right? So, because like I said, the mempool is finite. If you are running Bitcoin Core or any of its forks that refer to the standard policy, then it's 300 MB. What if a transaction has 50 descendants and all of them put together are of 500 MB? Then the entire cluster obviously cannot enter the mempool because the mempool is worth 300 MB and the cluster is now worth 500 MB. What do you do then? In that situation, you bifurcate the cluster into chunks, into smaller chunks such that those chunks fit into the mempool. And then you organize those chunks in the mempool in the form of highest fee. So the chunk that pays the highest fee gets priority to get included in the block, right? So it's at the apex of the queue, and then the next chunk that is paying the lesser fee, and then the next chunk that is paying the lesser fee, and then the chunk that is paying the least fee gets at the bottom of the queue in the mempool, right? So this is what cluster mempool is, to get rid of the ancestor descendant topology and to organize and bifurcate transactions in the form of clusters depending on their lineage, and then further bifurcating those clusters into chunks to ensure that chunks fit into the mempool, and then linearizing or linearly arranging those chunks into the mempool in descending order of their fees. So the chunk that pays the high fee goes at the top, and the chunk that pays the lowest fee goes at the bottom. That's what cluster mempool is. And this is believed to be, experimentally, it is believed that the cluster mempool is more profit maximizing. So if we refer to the contemporary ancestor descendant limit of accepting and rejecting transactions from the mempool, uh, it it has like a more variating output. So at times you might reject a set of transactions from the mempool which were more optimizing, which were more fee optimizing for the miners. So there are, the current or the contemporary mechanism is slightly more error prone, and experimentally it is believed and claimed that cluster mempool is more profit optimizing and is a more robust solution to linearly arranging clusters or chunks in the mempool in their descending form of fee rate, meaning the one that pays the highest fee will be at the top of the queue. That's what cluster mempool is. Now, what this article talks about is that obviously there are multiple algorithms that we can do this, right? We need an algorithm in place that will ensure that the chunk with the highest fee is at the top of the mempool, and the chunk that pays a fee lower than that is below that, and the chunk that pays a fee lower than that is below that, right? And there can be multiple ways to do that. In computer science and mathematics, that can be there can be multiple algorithms that can do the same thing, right? If you study data structures and algorithms, you know that you can sort the same data with multiple algorithms depending on your need, right? So there are multiple algorithms that can sort that data, but depending on your need and other factors, you choose which algorithm you wanna refer to. So likewise, there can be multiple algorithms which can linearly organize these chunks in the mempool. It depends on which one suits you, which one has what trade-offs. So there is a proposal that were made by Stephen Richer to delving Bitcoin about a research paper from 1989. He found that has proven algorithm that can be used to efficiently find the highest fee rate subset. So there's a research paper that was printed or published in 1989, and this person by the name of Stephen Richer found it. I believe they found it on DeepSeek. They were doing some research on DeepSeek, and they found this 1989 research paper, which has an algorithm that they believe is an optimal algorithm for arranging or finding the highest fee rate subset of group of transactions that will be topologically valid if the subset is included in the block. So they have found a 1989 a research paper that was published in 1989, and also its C++ implementation that they believe is optimal to arrange transactions in the order of the highest fee rate in the mempool, thereby optimizing the revenue that the miners generate. Whoever wants to read what that implementation is and what the research paper is can go and do so. The gist that we can cover in this section is that we understood what is the current mechanism in which transactions are arranged in the mempool. We understood what cluster mempool is. We understood what chunks are, and we understood the fact that Stephen Richer has found in a 1989 research paper in which there is an algorithm, and also found in C++ implementation that they believe has the most optimal solution to efficiently arranging the highest fee rate subset transactions in the mempool to optimize miner revenue. For those who are more interested in delving into more details, can read the post itself or the C++ implementation. If anybody has any questions pertaining to this, please feel free to unmute yourself and ask the question or post in the chat. We probably have 10 to 15 minutes left with us, in which we will try and go through the early update. And I don't think we'll be able to incorporate anything other than that. Anything, anyone? Anything in the chat? All right, cool. Cool. Okay. So we will talk about the early updates. That will probably be the final content that we will cover. Let's read through it first. Sergi Delgado made several posts to delving Bitcoin about his work over the past year implementing only for Bitcoin Core. He starts with an overview of how existing transaction relay called fanout works and how Ole proposes changing that. He notes that some fanout is expected to remain even in a network where every node supports early, as fanout is more efficient and considerably faster than set reconciliation, provided the receiving node does not know about the transaction being announced. Using a mix of a fanout and reconciliation requires choosing when to use each method and which peers to use them with. So the research has focused on making the optimal choices. Okay, so first we need to know what early is. We need to know what fan out is. We all know that Bitcoin is a peer-to-peer network. We all know that Bitcoin is a gossiping network. We all know that nodes communicate with each other, nodes interact with each other. Bitcoin nodes constantly share information with each other. Now, what is that information that these Bitcoin nodes share with each other? Primarily, they share transactions. So the moment a Bitcoin node sees a transaction, it validates that transaction and it relays that transaction to its peers. They also relay blocks. So whenever a Bitcoin node finds a block, they validate that block and then they announce that block to their peers. And then addresses, right? So whenever a new Bitcoin node is, for instance, being bootstrapped, it is in search for addresses, right? So the peers with which it establishes connection on the network share Bitcoin addresses with it. So three important or primary pieces of information that Bitcoin nodes gossip with each other on the network are A, transactions, B, blocks, and C, addresses. Now, how does this process work? Like, how do Bitcoin nodes share this information with each other? The contemporary mechanism of doing that is known as fan out. So if someone asks you how do Bitcoin nodes share transactions with each other, they share the transactions with each other through a mechanism which is known as fan out. What is fan out? It is just sharing that information with all your peers. So the moment your node sees a transaction, your node performs validation checks on that transaction. And once your node validates the transaction, it announces it to all of its peers, except the peer which shared that transaction with your node at first. So if some other node shared a transaction with your node, then your node already knows that the initiator node has that transaction. So it doesn't make any sense for you to share that transaction again with the initiator node. But other than that, you share the transaction with all your peers, irrespective of whether they know that transaction or no. So your node does not check whether your peers have that transaction already or no. It will just announce it. So there is a possibility that a lot of your peers already have that transaction. Still, you're relaying it to it, right? So if you have ten nodes with whom you have a connection on the network, you see a transaction for the first five. Let's assume you validate that transaction. Out of those 10 peers, the peer that sent you that transaction in the first place, you will not send that transaction back to that peer. But the other nine peers that you have, you will announce that transaction. You will share that transaction with all those nine peers. Even if all those nine peers already know that transaction, are already aware of that transaction, you will still share that transaction with all of your nine peers. Now, what does this do? This obviously adds redundant overhead for the network, right? Because every single time you're broadcasting a transaction, that transaction is broadcasted across the network, right? So you're utilizing common resources like bandwidth. You're utilizing common resources like network bandwidth. So you are wasting bandwidth of of the entire network, right? There are thousands and thousands of Bitcoin nodes right now, and every single time a node gets a new transaction, it validates it and it shares with all of its peers. And then all of the peers share them with all of their peers. And then all of their peers share them with all of their peers. Now, there is a huge possibility that a lot of peers already know that transaction, and despite that, you are sharing that transaction again and again and again, thereby wasting the bandwidth and adding latency because the more data that you are broadcasting, the more data that you are transmitting across the network, the more validation work nodes have to do, and the more bandwidth is usurped. So you are wasting common resources. Ideally, you don't want to share transactions with your peers who are already aware of that transaction. So that is where early comes into picture. What does early do? Early basically we bifurcate our peers on the network into two sections, right? Inbound peers and outbound peers. Outbound peers are those peers with which we establish a connection. Inbound peers are those peers who establish a connection with us. We control who our outbound peers are. We can handpick our outbound peers. We decide who our outbound peers can be. As for the inbound peers, we don't control them. right? Anybody can establish a connection with our node. So we don't control our inbound peers, we control our outbound peers. And the limit for the outbound peers, the standard limit for the outbound peers for Bitcoin Core is currently 8. So you can have 8 outbound peers, and the rest of your peers will be inbound peers. You choose who those 8 outbound peers are, you can't choose who your inbound peers are. With the contemporary mechanism, what Early proposes is that you do a fan out announcement only with your outbound peers. So you have 8 outbound peers. Every transaction that you receive, you validate that transaction and you announce that transaction with all 8 of your outbound peers. Okay, I'm just using this number 8. You can have less than 8 as well. You can even have more than 8. But 8 is the standard limit. So you announce a transaction with all 8 of those peers, except the peer obviously that has shared that transaction with you in the first place. But all your inbound peers, you don't announce the transactions with them, right? You don't announce your transaction to them. Rather, you indulge in set reconciliation. What is a set reconciliation? At regular time intervals, you you take the set of transactions that your inbound peers are aware of, and you take the set of transactions that you are aware of and you reconcile them. And whatever transactions that your peers are aware of, your inbound peers are aware of, and you are not aware of, okay, you ask for those transactions. And whatever transactions that you are aware of and your inbound peers are not aware of, you give those transactions to them, right? So currently, how is it happening? You announce each and every transaction to all your peers, to your inbound peers, to your outbound peers, except for those peers who have already initiated and shared that transaction with you in the first place. But what does early propose? Early propose that you will only announce the transaction to all your outbound peers. Okay, the fan out mechanism will be specific to your outbound peers. But for your inbound peers, you will not announce the transactions with them. At regular intervals, you will just do a set reconciliation. You will ask them for the set of transactions that they are aware of. You will take the set of transactions that you are aware of and you'll compare, you'll reconcile. So whatever transactions they are not aware of, they will individually ask for it and you will give them. And whatever transactions that they're aware of and you're not aware of, you will ask them individually and they'll share it. What happens is that you will never share a transaction with any of your inbound peers that they are already aware of, and your inbound peers will not share transactions with you that you are already aware of, thereby reducing bandwidth. And uh, like tests that have been done in adiabatic conditions have proven that this can reduce the bandwidth consumption by almost more than 90%. So 90% of the bandwidth consumption currently on the Bitcoin network that is being used up by transaction announcement through the fan out mechanism can be reduced, thereby obviously reducing overheads of the nodes and the bandwidth consumption, which is the common resource of the network. This is what Olay is. Okay, so we talked about what fan out is and we talked about what Olay is. Olay basically combines between set reconciliation and fan out. Currently, we have fan out for inbound and outbound both pairs. Olay does fan out only for outbound pairs, and for inbound pairs, it does set reconciliation. So there are some proposals that have been made, or some progress that has been made by the developers that are working on earlier. Let's just go through them quickly. We'll read them. Using a mix of fan out and reconciliation requires choosing when to use each method and which peers to use them with. So his research has focused on making the optimal choices. Filtering based on transaction knowledge examines whether a node should include a peer in its plans to fan out a transaction, even if it knows that peer already has the transaction. For example, our node has 10 peers. 3 of those peers have already announced the transaction to us. If we randomly choose 3 peers to further fan out that transaction, should we select from all 10 peers or just the 7 peers that haven't announced the transaction to us? Surprisingly, simulation results show that there is no significant difference between the options. Delgado explores the surprising result and concludes that all peers should be considered, that is, no filtering should be done. So, if you select a certain subset of your peers with whom you want to indulge in fan out transaction, let's say you have 10 outbound peers and you decide that you want to do fan out only with 3 of those outbound peers. What should be criteria to determine which those 3 peers are? Is it that you always look at the peers that already have that transaction and you exclude them? So out of the 10 peers that you have, 3 already have that transaction. So you exclude those 3 and you take into consideration the remaining 7. And from those 7, you announce fan out to any 3 peers. Would that be more optimal and efficient? Prima facie, that's how it looks like. But results that this developer conducted have led him to believe that it doesn't make a lot of difference whether you exclude the peers that already have that transaction and only include the peers that don't have that transaction, and you choose three out of them and you indulge in fan out, or whether you choose from the entire subset of 10 peers and you relay transactions to any three out of those 10 peers via fan out, the results are more or less the same. Like the bandwidth consumption of the network is more or less the same. The latency is more or less the same, which is quite now an alarming discovery, I would say. The second assumption, observation, or proposal is when to select fan out candidate peers. Examine whether node should choose which peers will receive a fan out transaction, with the remainder using early reconciliation. Two options are considered shortly after a node validates a new transaction and queues it for relay, and when it's time for that transaction to be relayed. So, when should the node choose which of its peers it will indulge in fan out with, and which will it indulge with in earlier reconciliation? Now, there are two options. Firstly, shortly after a node validates a new transaction. So, usually, when a node sees a new transaction, it validates that transaction. After validating the transaction, it does not immediately broadcasts it. There is a buffer in. There is a small buffer in. This is for privacy reasons. So, when should the node determine which peers it wants to indulge in a fan out? Which should it decide that immediately after validating a transaction, or should it decide after that buffer is over and when it is in a position to relay that transaction? So the results suggested that there is no major difference. Two options are considered shortly after a node validates a new transaction and queues it for relay. And when it's time for that transaction to be relayed, nodes don't relay transactions immediately. They wait a small random amount of time to make it harder to probe the network topology and guess which node originated a transaction, which would be bad for privacy. Again, simulation results show that there are no meaningful differences, although the results may vary in networks with partial early support. So there's no major difference whether you choose your peers with which you want to indulge in fan out immediately after validating the transaction, or you wait for a time buffer and choose your peers with which you want to indulge in a fan out relay just before relaying the transaction. There is no major difference. I'll take 5 more minutes of your time at the most. Or we'll just leave this section. Okay. The fourth one you all can do on your own. We'll just leave this one because we're already at 9:05. We're way past the, not way past, but at least 4 minutes past the 1 minute mark. How many peers should receive a fan out? Examines the fan out rate. A higher rate accelerates transaction propagation but reduces bandwidth savings, right? So, how many peers do you want to indulge in fan out with? If you indulge in fan out with a lot of peers, then the propagation, I mean, it reduces the bandwidth savings, right? Because you're relaying redundant information. Your peers who already have the information, you are again and again sharing that information with them. So it reduces the bandwidth saving, even though it accelerates the transaction propagation, meaning more and more nodes on the network will be informed about a transaction, but at the trade-off of bandwidth savings. Besides testing the fan out rate, Delgado also tested increasing the number of outbound peers, as that's one of the goals of adopting early. The simulation shows the current early approach reduces bandwidth by approximately 35% using current outbound peer limit 8. So currently the outbound peer limit is what? 8 for Bitcoin Core. And if you stick to that limit, and then the early reconciliation mechanism reduces the usage of bandwidth by what? By 35%. And 45% using 12 outbound pairs. So if you increase the limit from 8 outbound pairs to 12 outbound pairs, then the bandwidth saving is 45%. However, the transaction latency is increased by about 240%. Many other trade-offs are graphed in the post. It doesn't mention the number of peers. However, all right. So if you increase the number from 8 peers to 12 peers, then the bandwidth reduce bandwidth by approximately, okay. The simulation shows the current early approach reduced bandwidth by approximately 35% using current outbound peer limit of 8 peers and 45% using 12 outbound peers. However, the transaction latency is increased by 240%. Okay. So with 8 peers, you say 35% of bandwidth. With 45 peers, if you use early, you with 10 outbound peers, if you use only you save 45% of bandwidth, but the latency increases. Why? Because you have to reconcile. At regular intervals, you will have to ask your peers for the set of transactions that they're aware with and reconcile with the set of transactions that you're aware with, right? So this is a time-consuming process, and thereby it induces latency. So only basically reduces the bandwidth, but it increases latency. It's a trade-off. So it depends on to what extent you want to reduce the latency and to what extent you want to compromise on the to what extent you want to reduce the usage of bandwidth and to what extent you want to reduce the latency. To what extent are you okay with this trade-off? You make a decision. So many of the trade-offs are graphed in the post. In addition to the results being helpful for choosing current parameters, Tulgado notes that they'll be useful for evaluating alternative fan-out algorithms that might be able to make better trade-offs. So you can, I guess, click on this and see the different permutations and combinations with how many peers the bandwidth is uh, reduced and with how many peers the latency is increased and the different A to B testing that was done. So this is what we'll be able to cover in this section. For those of you who are interested, can go through the consensus changes where they talk about LNFML anchors and what should be the steps of the LNFML anchors and this new opcode that is proposed, emulating operand, and the discussion about lowering the minimum transaction relay fee and the consensus changes, code and documentation changes, and releases and release candidates. As I mentioned, that this is quite a lengthy newsletter that we will not be able to cover, but we got together with the intention of at least trying and discussing the few topics that might be of interest to us. And if somebody wants to delve into it into more detail, then they can do that at their own time and convenience. And if you have any questions, any queries, please feel free to shoot them my way in the chat section or unmute yourself, or even feel free to post on Discord. We'll be more than happy to help you out. Somebody said something. Korgo, thanks for the session. You're most welcome. All right. Good night. Take care, everyone. Thanks a lot.